today to listen to your presentation about your thesis. I will first present the member of the jury. You know already, I suppose, the two reviewers because you received their report.
Yes.
And they are online. Donc, Jérôme Chevalier and Professor Kenneth Dalgarno from the University of Glasgow and Jérôme Chevalier from University of Lyon.
Yes.
The other member of the jury are Mr. Joël Alexis from the unit DARD. You have also Mr. Luca Luzzardi from University of Modena.
Yes.
He is also online. And there is myself. You know me very well. I imagine after 3 years of the urban project. And then your supervisor, Mrs. Menderpo, Mr. Lagocosa, and Mr. Pascal. You have between 45-50 minutes to present your work.
Thank you so much. Thank you, Professor Lerish, for your introduction. Today, I will be presenting my thesis work, which was carried out in Sirimat Laboratory in Toulouse. And this thesis work is also part of an European project, which is called DAC 3D printing. This project gathers 14 PhD students with numerous academic and industrial partners to develop additive manufacturing solutions for ceramic applications. 5 work packages work collaboratively to transfer scientific knowledge into applicable industrial applications. As a member of the design product work package, my role in this project is to develop additive manufacturing approaches to fabricate ceramic metallic multi-materials for applications such as aerospace and biomedicals. What's additive manufacturing? Additive manufacturing is a group of processes that create 3D objects layer by layer by following a digital design data. According to ISO ASTM joint standard, additive manufacturing can be divided into 7 subcategories. And this division is mostly done based on the feedstock used, for example, a powder or paste, or the energy source used, such as UV light or the laser. In today's presentation, the main consideration will be powder bed fusion technologies, and among those technologies, selective laser melting and sintering. In a commonly accepted design for a SLS SLM machine, there are 4 fundamental parts: the powder tank, building platform, powder spreader, and the energy source laser. In a workflow of SLM process, the building platform goes down and creates space for the newly coming powder layer. And the piston underneath the powder tank goes up and feeds the system with a certain amount of powder. The spreader spreads the powder on the building platform side, and once the powder layer is ready, the energy source selectively sinters or melts the powder particles to each other by following the directions coming from the digital design data, specifically for this layer. As this continuously keeps happening, the 3D object is finally formed. In the review that we published in Open Ceramics in 2021, we proposed a name change to SLS SLM as powder bed selective laser processing. Instead of going mechanism separation like sintering and melting, by just focusing on the process itself. So the acronym PBSLP will be used in this presentation to refer this process. Due to their good compatibility, metals and polymers are commonly used in PBSLP. For example, very complex shaped metal pieces can be fabricated with this method due to its design flexibility. Or on the other hand, personalized prototypes can be fabricated in a very short time by using polymers, as we see here for a jaw replacement operation, for example. And when we check the number of publications in the literature that are focusing on PBSLP, we see that majority of them are using metals, polymers, and composites. Only 8% of studies are focusing on ceramics. So what makes them, especially white oxide ceramics such as alumina or zirconia, limited for this process? The first limitation is their low energy absorption, especially under Nd:YAG laser wavelength. Another limitation is their low thermal shock resistance, which is a problem in a process where a very high temperature, very high energy is transferred to material in a short time. And also their very high melting and sintering temperature, which is quite challenging to reach in a limited time as well. To overcome these three issues, various strategies were applied in literature. For example, Wilkes et al. In 2013 aimed reducing the thermal gradients between cooling and heating by introducing a preheating system in their PBSLP machine. The preheating was applied at 1600 degrees to building platform, and at the final pieces almost with 100% relative density were obtained. In another study carried out in Belgium Ceramic Research Center, alumina powder was combined with graphite as an absorbency enhancer, and after PBSLP process, the density of pieces was around 85%. And then a thermal treatment, a post-treatment was applied to the pieces, and relative density was increased up to 90%. In another approach applied by Chen et al., ceramic powder was mixed with epoxy resin, and PBSLP was used only to process the polymer inside the mixture to create green bodies. And then to sinter the particles which were embedded in the polymer, post-sintering process at 1500 degrees for 2 hours were applied, and pieces with relative density of 86% was obtained. Between 2015 and 2018, Loic Ferrache, who was a former PhD student in Cerimat laboratory as well, he conducted another thesis work to fabricate zirconia pieces with direct PBSLP approach. As my thesis work is a continuation of this study, I believe that a detailed information on that study is needed. Pro X200 from 3D Systems was used as PBSLP machine, and this machine is equipped with an Nd:YAG laser, which has spot size of 30 micron. And this spot size can be adjusted up to 40% by the focalization option. And this PBSLP machine allows users to perform their studies in air or room atmosphere or inert atmosphere. Powder bed compaction is possible with the help of a roller drum in this process, and pre and post heat treatment within the machine is not possible. The software, the design software comes with this equipment, provides 5 different lasing patterns, which are normal pattern, grid, inward, outward patterns, and hexagonal island pattern. So in that specific study, room atmosphere was used in all the experiments, and no defocalization and pre or post-thermal processes were applied. 8 mol per centimeter stabilized zirconia and powder was used in this study. It was provided from Tozor with almost perfectly spherical shape and almost full density inside with a good flowability, which is adapted for this process. And this powder was completely made of cubic phase zirconia. However, there was a limitation with this powder. It's laser absorbency under Nd:YAG wavelength. To overcome this issue, the ceramic powder was mixed with 0.75% weight percent graphite in a turbula shaker physically. And then after this enhancements process, the absorbency was increased up to 60%. And the flowability was not affected by this enhancements process. Once the powder was ready for operation, laser meter interaction parameters were also needed to be fixed. Parameters such as laser power, lasing speed, layer thickness, and hedge distance, which is the distance between 2 parallel lasing tracks, fixed after optimization processes. And solid, self-standing, visually corresponding to design data 8YOC pieces were possible to fabricate with energy density of 240 joule per cubic millimeter. Once the pieces were fabricated, there were some limitations remaining. For example, on dimension, there were some limitations for upper limits to produce big pieces. And also going for complex shapes was challenging as well to obtain cavities, hanging structures, for example. And also, even though 8YOZ is commonly used for thermal applications such as thermal barrier coatings, there was a need for widening the application area. Once solid ceramic pieces were fabricated, their combination with metals as multi-material was intended as well. And for this, aluminum silicon 12 alloy was preferred to be used as material part of the metal part of the multi-material. And to do that, firstly, in a single step, the metallic pieces were fabricated within the same PBSLP machine. And then by only changing the metallic powder with ceramic powder, the ceramic pieces were deposited, fabricated directly on the metal parts. So by this, in a single step, in a single machine, the multi-material were obtained as shown in the example. After both side of studies, there were some questions remaining. And as the main objective of my thesis work as well, I was looking for answers to these questions separately as ceramic parts and the multi-material parts. So after this part of the presentation, I will be trying to answer questions for the first ceramic part, and then I will come back to the multi-material part. So the first question remaining for the ceramic parts was, is this optimized parameters for 8YOZ? Is it possible to use them for other ceramic materials? We talked about 8YOZ, about its applications, and I was looking for widening the application area, and I wanted to go for biomedical applications. And to do that, I was looking for possible options. And alumina toughened zirconia, which is also much better thermal shock resistance than 8YOZ, was a good candidate. And from the same company, from Tozo, very similar morphologic powder was supplied. As we can see here, they are both spherical, almost fully dense, and has similar flowability. And alumina toughened zirconia was a good candidate for this process. However, due to its different chemical composition, a new lasing optimization was needed. As their morphology, flowability, and laser absorbency is very similar, I took the energy density needed for 8YOZ fabrication as a reference point. And I kept layering parameters stable as well, because they have similar morphologies. And I create 26 different combinations between laser power and lasing speed to try energy density windows lower than 240 and higher than 240 degrees. To evaluate the pieces that I fabricate with these windows, I apply 3 different criteria, which are pieces are existing on the platform, corresponding visually to the CAD data, design data, and pieces are defect-free. So when we check the energy density is higher than 240, and we check the 240 firstly, we see that pieces exist on the platform. However, with all the other pieces in the same platform, they don't match the design data, and they're full of defects. When we check the energy density window below 240, a combination of lasing speed and lasing power was giving pieces that satisfy 3 of the criteria. So I accepted this energy density value and this combination suitable for ATZ fabrication. And when I go for upper limits, ATZ pieces larger than on surface area and higher than on the Z direction, than 8YOZ was possible to fabricate. When we go upper limitations, very big pieces, solid pieces were possible to fabricate, and also complex shapes with inner cavities and hanging structures were possible to fabricate as well. So we can answer the first question here. yes, with the re-optimization of lasing speed and lasing power, similar fabrication patterns can be used for a new material such as ATZ. So the second question was, what's the dimensional limitations and accuracy for this newly produced ATZ pieces? To test that, I produced two different pieces with two different shapes, and I compared the design data values with the measurements I did on the solid pieces. What takes attention first is for all the type of and all the size of pieces, there's an enlargement on both surface area and the height. And the dimensional accuracy on the surface area is between 87% to 95%. And the dimensional accuracy on the height is around 98% for two type of pieces. When we see the dimensional accuracy on a graph, we can see that the dimensional accuracy is increasing with increasing surface area. However, the dimensional accuracy on the height is being stable with increasing piece size. So one explanation for this can be the laser matter interaction. When the laser hits the surface, it creates a heat-affected zone. And when the laser is processing the corners of the piece, and also when we consider the spot size of the laser, the neighboring powders might be being affected by this heat. And they can be included in the piece with sintering or necking between powders. So as we can see here in the illustration and the observations. So we can say that for the second question, ATZ pieces with good dimensional accuracy can be fabricated. However, we still have sublimits for fabrication of ATZ pieces. It was challenging to fabricate eight ATZ pieces with surface area of 44 square millimeter. The third question for the ceramic part consists of three sections. What's the effect of fabrication on the morphology? What's the effect of fabrication on microstructure and the crystalline structure? Firstly, I tested the effect of lasing pattern on the morphology. And for 8YOZ fabrication, only normal and hexagonal island strategies were giving satisfying results. And when we compare them to each other, the normal strategy gives a higher surface roughness than hexagonal strategy pattern. And for ATZ, only working pattern was hexagonal island strategy. And when we compare two different materials fabricated with the same strategy, hexagonal strategy, we see that ATZ pieces has lower surface roughness than 8YOZ pieces. One explanation for this can be the melt pool, which is created during lasing process. As the energy density needed for ATZ fabrication is almost half of 8YOZ, it might be creating less depth of melt pool, and that can be decreasing the surface roughness on ceramic pieces. When we check the effect of fabrication pattern on the cross-section, vertical polished cross-section of pieces, I first compare 8YOZ pieces fabricated with two different strategies. And these images, these scanning electron microscopy images, when I process them with image analysis software ImageG, I see that the porosity in hexagonal pattern fabricated piece is almost 4 times of the one fabricated with normal strategy. And also what takes a significant attention here is the cracking pattern in two pieces. In one, the cracks are more parallel to fabrication direction and more narrower. And they show 3 different distribution in the microstructure, like close to surface, in the core and close to building platform. And on the other hand, we have larger cracks, which are going through almost the entire structure and ending up in the surface. When we include the ATZ pieces fabricated with hexagonal pattern, we see that cracking is shorter, kind of homogeneously distributed through the structure, and they are more narrower if we consider the defects as well. So the porosity obtained for this piece was around 7%. The next effect was checking the hatch distance. And for 8YOZ pieces, except 50, which was kept stable during process optimization, hatch distances 60, 70, and 80 was also working. And the most significant change was observed on the surface roughness. We see that surface roughness is increasing with increasing hatch distance. The relative density of pieces were remaining stable with increasing hatch distance. When we apply different hatch distances on ATZ fabrication, we see that except 50 micron, none of the hatch distances are giving satisfying results by having pieces defect-free, full of cracks, and most of them showing full of defects. So we can say that here, for 8YOC fabrication, we have a wider parameter area, two strategies, normal and hexagonal, for hatch distances, while we have only one pattern and one hatch distance 50 micron working for ATZ fabrication. So the next question was, what was the effect of fabrication on the crystalline structure of pieces? Here we see that first the powder of 8YOZ and ATZ before the lasing process, and then we compare them with the solid pieces after fabrication. For 8YOZ, the first thing that takes attention is remaining cubic phase. As no new peaks appear or any peaks disappear, we say that, and by comparing the database of XRD, we say that the cubic phase is remained. When we stack these patterns on each other, we see that there is a narrowing of the peak for the fabricated pattern. And when we calculate the crystalline size with Scherrer equation, this narrowing was indication of the crystallite growth. And we see that after calculation as well. When we check the ATZ before and after fabrication, the most significant change is the disappearing of monoclinic phase which appear in the powder and that we cannot observe in the solid piece. The solid piece was completely tetragonal phase zirconia. And the same narrowing of the peaks was observed for ATZ as well. And when we calculated the crystalline size, we see crystalline growth also for tetragonal phase and alumina inside the ATZ as well. So what can be the reason of this crystalline growth is most likely the melting, or while upper layers are processing, the heat affected zone is causing like repeating heating in the lower layers, and that cause enlargement of growth of the crystals. So when we calculated the relative heat intensity of phases in ATZ pattern, we see that monoclinic phase completely disappears from the structure. One explanation for this can be explained on the phase diagram between zirconia and yttria. The composition might be going to complete melting, and during cooling down, due to fast cooling or quenching, the composition might be stable in the metastable phase of tetragonal phase. And we can answer the second part of the third question here. The crystallite growth is observed for both materials, and while fabrication is not causing phase change in 8YOC, fabrication caused disappearing of the monoclinic phase in ATZ structure. So when we observe the cross-section of ceramics with scanning electron microscopy, we see that for 8YOZ, two microstructures appearing in the observed zone. The first microstructure is mostly distributed through the structure with the coarse grains, and the second microstructure is mostly in an elliptical shape that is appearing locationally inside the first microstructure. So to see the distribution of elements in these microstructures, I run an EDX elemental mapping. And when I overlap all the elements to each other, we see that there is 8YOZ everywhere inside the microstructure. So the first and second microstructure that we identified having same composition with different morphology. What was unexpected here to find aluminum and oxygen in this composition in some specific areas. So when I checked ATZ, similarly, we identified 3 microdiffractions with fine, middle, and coarse grain sizes. And when I run a similar elemental mapping, I figured out that the composition is still homogeneous. There's ATZ distributed everywhere. The only difference is the size of grains in these 3 microstructures. And the third part of the third question, the reason of this changes in the microstructure while they have the same chemical composition might be due to locational varying cooling rates and their cooling speed. So to conclude the first part for ceramics, we can say that very complex shaped ATZ pieces with very high relative density can be fabricated. And also we have a larger parameter window that works for 8YOZ based on the pattern and H distance. And also, as there is no phase change for 8YOZ, we observe the disappearing of monoclinic phase in ATZ structure, and an irregular microstructure observed for both materials without a change in their chemical composition. So after answering these 3 questions for the ceramic parts, I want to come back to questions remaining for multimaterials. And I can say that with this optimized parameters for ATZ after 8YOZ, it was possible to obtain new multimaterials with the same method by including the ATZ in the structure. So the first question can be answered here direct forward. So the second question is, what's the chemical and mechanical bonding mechanism in this ceramic metallic joining? To answer that, I take a cross-section, vertical cross-section of multimaterials, and when I observe them with scanning electron microscopy, I observe 2 interfaces for 2 multimaterials. And then with higher magnifications, we see that the borders of these 2 interfaces are quite easy to separate from the rest of ceramic and metallic parts. And when we come closer to these magnifications, we see that there is grading in this microstructure. So at the highest microstructure imaging, I see that this microstructure is completely different than the ceramic and metallic part itself. So to check what are those microstructures and what's the elemental distribution in these microstructures, I again run an elemental mapping on these microstructures again. And I checked 4 different elements coming from ceramic and the metallic part. So before overlapping these elements, I had to change silicon from yellow to blue because yellow is also mid color. So to prevent confusion, I had to identify with blue. And when I stack these images, I see that some purple areas, which is a mixture of red and blue, which is the mixture of zirconium and silicon, appear in the microstructure. So that was very interesting to see that because zirconium is coming from ceramic and this silicon is coming from metal. So for me, that was the first indication that a chemical interaction is occurring between the ceramic and metallic part by 2 different elements existing in the same area. Another interesting outcome from this measurement was inability to detect yttrium in this area. As yttrium is used as a stabilizer in zirconia structure, it's surprising to not detect yttrium here while zirconium is existing in the interface. So this characterization made 3 main questions in my mind, which are what's the depth of interaction of these elements, how far they go, where is yttrium, what happens to yttrium, and which new phases occur among these unexpected elements. To answer these 3 questions, I used 2 methods, like microprobe analysis and micro-XRD. Electron microprobe analysis to make a point-by-point elemental analysis, I follow experimental flow where we point-by-point study the elemental composition, where we reduce the gap between 2 points when we come close to the interface. So here we see the elemental distribution of 2 interfaces, the first one up row and the second one in the bottom row. And I want to come quickly to interface itself. We see that the interface distance, which is observed in scanning electron microscopy, is also corresponding with electron microprobe as well. And what's interesting, just after the 0 point, the estimated 0 point, which is the border between ceramic and interface, yttrium which is indicated with blue in the graph, disappearing from the composition, going to 0 directly. We observe this for second interface as well. So yttrium was not also detected in this method. So when we come back to large scale and when we check the detection of aluminum, metallic aluminum, we said up to 600 micron in the ceramic side, metallic aluminum can be detected. For the second interface, even though there is alumina and naturally aluminum inside this composition, we see that approximately up to 300 micron, the aluminum can be detected in the ceramic structure with a higher weight intensity. So to answer the second part of the question, what are the possible phases occurring in this interface, I perform micro XRD analysis as well. And to do that, I follow a path full of points, measurement points of 25 points with gapping of 100 micron, starting from the ceramic part, going to metal, with passing through in the interface. So when I check the XRD pattern of all these points, I see that 2 points are corresponding with the interface 1. So when I check the possible phases by comparing the peaks with XRD database, I see that an intermetallic phase between zirconium and silicon, and also a ternary phase among aluminum, silicon, and zirconium appears in the structure. When I check the second interface, there is only 1 point corresponding to interface, which is shown with gray color. There was also the ternary phase of aluminum, silicon, and zirconium. However, the creation of these interfaces and its creation mechanism was still a huge question mark. To answer that, I run an experimental procedure where I deposit 1 to 25 layers of ceramics on metallic substrates, and then I take XRD patterns of each sample from the top surface. Then I stuck this XRD patterns on top of each other, and from first layer to 25 layers, I follow the changes in the XRD pattern. So for the first interface, we can say that starting from the first layer up to 7th layer, we observe the creation of intermetallic phase and the ternary phase. And after the 7th layer, the composition goes exactly like ceramic structure. After that, for the second interface, we also see the creation of this intermetallic phase and the ternary phase for the first 5 layers. And after this 5th layer, the composition goes as ATZ structure. So this part can be concluded as for first interface, it takes 7 layers for interface to appear. And for the interface 2, it's first 5 layers. However, there are still some questions remaining. For example, what's the exact composition of this ternary phase, which was detected in microdiffraction analysis, and also still yttrium, in which form yttrium appears or disappears from the structure. To answer these questions, I wanted to run a TEM analysis, but for TEM, first I had to extract a lamella from my both interfaces. As we see with areas circled with yellow and arrowed, from interfaces, we removed a lamella with a certain thickness by help of a FIP technology. And when we observe lamellas with two different detectors, which is only a secondary electron detector, and the other one is a detector that combines a backscattered electron and secondary electron detector, we see that for both lamellas, rounded shaped formations appear in the lamella. So as this lamella exactly corresponds to the interface, I wanted to perform another elemental mapping on high magnification. And for two interfaces shown side by side, we can see the intermetallic phase between zirconium and silicon, where only silicon and zirconium appears, but aluminum not appears in both interfaces. And the ternary phase, as three of them, silicon, zirconium, and aluminum, appears in two structures. However, there were some point-shaped areas observed where there is aluminum, oxygen, and yttrium, which was indicated with pink circles. The composition and situation of these circles was still remaining as question mark. So I increased the magnification again, and I specifically studied these dot-shaped areas. And what I see, these dots actually are aluminum, yttrium, and oxygen-rich areas where there is no silicon and zirconium. When I compare the existing elements with the phases that I detect in microdiffraction measurement, I see that for the first interface, the ternary phase is appearing in one area, the intermetallic phase is appearing in one area, and aluminum and silicon is appearing in different areas. However, there is no any phases detected, including aluminum, yttrium, and oxygen, was shown in microdiffraction measurements. So what I do is here I choose a method that I can study the crystallinity of these phases appearing in the structure. And when we choose two areas, one is aluminum, oxygen, yttrium rich, and one is the ternary phase, and used selected area electron diffraction, I see that while the ternary phase is giving diffraction patterns, the yttrium rich circular area is not giving any diffraction patterns. So that means this structure is amorphous. That might be the biggest indication that it's not detected in XRD measurements. So for the second interface, if we come back there, we again see some yttrium concentrated dot-shaped areas. And when I study them again, as we show here, aluminum, yttrium, and oxygen-rich areas, we again cannot see them in microdiffraction measurement. And there again, when we compare the aluminum, oxygen, yttrium-rich areas where the ternary phase appear, while the ternary phase is giving diffraction patterns, the yttrium-rich areas are not giving any diffraction patterns because they are amorphous again. So the question remaining still was, what's the exact composition of this ternary phase? To calculate the elemental atomic ratio of these two similar zones, two same zones, I needed two information: the thickness of this lamella and a density. Then I was able to calculate this atomic percentage of each element existing in this area. To calculate the lamella thickness, I used a model and a software that gives you the data of thickness. And then I took a reference structure to estimate the density of this ternary phases. So when I run the calculation to calculate elements, I see that the calculation I did is perfectly corresponding with the atomic values of elements that I detect in microprobe analysis. So that helped me to say that the reference structure I took for this ternary phase is, it can be a good candidate for the identification of this ternary phase. So I wanted to check if the creation of this ternary phase is possible or not in this phase structure, in this environment. When I take the elemental distribution from microprobe analysis and when I apply them on the ternary phase diagram between among aluminum, zirconium, and silicon, I see that the area is already corresponding to the intermetallic phase. And while cooling, the composition might be going through, as shown with red arrow, and it can meet the ternary phase area, which was accepted as a reference point. And due to fast cooling or quenching, it can be locked in this composition. So kinetically as well, appearance of this ternary phase and the intermetallic phase is possible. So if we want to conclude this second part, the multimaterial part, we can see that a chemical bonding between a chemical interaction and bonding between the metallic and ceramic part is created because we observed an interface. This interface is having a different composition by including a ternary phase and intermetallic phase, and it's different from both metal and ceramic parts. And also, one important outcome from this part was actually the interface, the interaction zone. It's larger than it's observed with some images, because we see that aluminum can be detected in ceramic part up to 600 micron in first combination, and up to 300 micron in the second combination. So to conclude the entire picture, the entire presentation, I can say that 8YOZ and ATZ fabrication is like a game of compromises. 8YOZ has a larger application area and larger parameters that can be applied to the ceramic powder. For example, more lasing pattern, more hedge distance, and that kind of patterns. On the other side, we can apply less parameter window to ATZ. However, with ATZ, we can obtain more complex shapes that we cannot obtain with 8YOZ. For the multimaterial side, we see that the first interface is thicker than the second one, and that was also identified in microprobe analysis as well. And very similar phases appearing in both interfaces, even though joining multimaterials are quite different than each other. And the appearance of the amorphous phase of among aluminum, yttrium, oxygen was observed for both interfaces as well. And the interaction depth is larger than as we explained, I'm sorry. So what would be the perspectives for this study? Can be, firstly, the mechanical testing of both sides, the ceramic fabrication as well, and also the joining forces between ceramic and metal parts in multimaterials. For ceramics parts, I would offer compression, tensile, and three-point bending test. And for the multimaterials, to check adhesion between ceramic and metallic parts, I would offer shear test and three-point bending test. And after a second step of perspectives, I would offer imaging of the interaction zone and also measuring the actual temperature of the interaction zone to understand much better which temperature we are reaching, what's the possible kinetics at this temperature, and that will be very helpful to understand the creation of phases in the structure. And this can be done by using multi-wavelength pyrometers or high-speed cameras, or with a combination of modeling, for example. And third and last perspective I would offer would be introducing new multimaterial combinations and their optimization for this process to widen the application area of multimaterials. For example, for ceramic parts, I would offer cerium stabilized zirconia or alumina and its derivatives, for example, for the ceramic part. And for the metallic part, I would offer titanium or cobalt chrome-based alloys. So before closing my presentation, I would like to thank all the members of the jury for taking their time to be part of this thesis defense, and also all the members of Cerimat Laboratory, INP Toulouse, and Université Paul Sabatier, and all for your attention. Thank you.
Thank you. now we have to include some question, ask some questions. But before, yes, I can thank you for this exact time for the business. So the first reviewer, we asked to Jérôme Chevalier. So 9, we have one question. Direct, we have to review the possibility to go.
Okay, thank you, Anne. Thank you, Mrs. President. Sometimes I hear well, Eren, but it was a bit more difficult to listen to you, Anne.